The distillation of alcohol-water mixtures to produce purified alcohol is an industrially important operation that is normally carried out in distillation columns. Here is a schematic of a distillation tray for separation of alcohol-water mixtures. The Murphy efficiency of such a tray is defined as the actual composition change in the vapor phase. Y is the mole fraction of alcohol leaving the tray. Y sub E is the mole fraction of alcohol entering the tray. And Y star is the composition of the alcohol that is in equilibrium with the liquid leaving the tray. So the Murphy efficiency is the actual composition change in the vapor phase divided by the composition change where the vapor leaving to be in equilibrium with the liquid leaving the tray. Now, for a liquid mixture of azeotropic composition, the vapor-liquid equilibrium is described by this relationship where Y star is the composition of the vapor phase in equilibrium with the liquid phase of composition Xi. And for an azeotropic composition, Y star equals Xi. For example, for ethanol water mixtures, the azeotrope composition is 0.87. For mixtures of 2-propanol water, the azeotrope composition is 0.623. And there is no driving force for vapor-liquid mass transfer if the composition of the liquid on the tray corresponds to the azeotropic composition. There are two technological solutions that are possible. The most commonly one that is used is to add an entrainer to alter the vapor-liquid equilibrium. And we have azeotropic and extractive distillation operations that are energy intensive. I want to discuss today a different technological solution, that is to distill in the presence of an inert gas and rely on the fact that the Murphy efficiency of component 1, alcohol, is different from the Murphy efficiency of component 2, water, component 3 being the inert gas. And this difference in the Murphy efficiency leads to separation of mixtures of azeotropic composition. The theoretical background to the material I will present is provided in two of my publications, both in Chemical Engineering Science, 2017, and another one in 2019. For background to the theory, also have a look at my video presentation, Murphy efficiencies, on my YouTube channel. In order to illustrate the principle of separating a mixture of azeotropic composition by allowing the azeotropic mixture to distill in the presence of an inert gas, let's consider a distillation tray. The liquid entering the tray is a 2-propanol water mixture of azeotropic composition. The tray is well mixed, and we bubble the tray with pure nitrogen that enters at the bottom. And we examine diffusion of 2-propanol, component 1, water, component 2, into a gas bubble that contains pure nitrogen. So this bubble would be near the entrance to the distillation tray. This is a ternary vapor mixture consisting of 3 components: 2-propanol, water, and nitrogen. The binary pair diffusivities are shown here. For 1,2, that is for 2-propanol water, the Maxwell-Stefan diffusivity is 1.47 times 10⁻⁵ square meters per second. For 1,3, that is 2-propanol nitrogen, the diffusivity is 0.9 10⁻⁵ square meters per second. For water nitrogen pair, D23, the diffusivity is 2.27 times 10⁻⁵ square meters per second. The water nitrogen diffusivity is the largest of the 3 values shown here. This is because water is the smallest molecule and has the highest mobility in this ternary mixture. So we have to determine the interfacial fluxes using the solution to the Maxwell-Stefan diffusion formulation. The details are provided in my publications listed here. And by solving the transient diffusion equations along with the Maxwell-Stefan diffusion formulation, we can determine the mole fraction of water to that of 2-propanol in this vapor bubble as the bubble rises through the liquid. And this ratio is plotted in this graph as a function of the contact time. We note that the ratio of water to 2-propanol in the inside the gas bubble is close to 0.9 at short contact times near the entrance to the tray. This is significantly higher than the azeotropic composition, which is about 0.62. With progression of time, the ratio of water to 2-propanol decreases and approaches the azeotropic composition. So if the contact time is limited to say 0.05 seconds, they will have a mixture here that is richer in water compared to 2-propanol as compared to the azeotropic composition. So we can break the azeotrope by distilling in the presence of an inert gas such as nitrogen. The concept of diffusion distillation, as sketched here, has been verified experimentally, and I refer you to my papers here for the appropriate references.